In this video, I'll be going over our notes on segment lengths in circles. The first theorem that we're looking at is called the Segments of Chords theorem. It states that if two chords intersect inside a circle, then the product of the lengths of the segments of one chord is equal to the product of the lengths of the segments of another chord. So we're going to be taking, if we look at this circle, the segment AE times the segment EB, so these two parts of this chord, if we cut them into two segments, when we multiply them, they should be equal to when we take the segment DE times the segment EC, the other two parts of the other chord that was intersected. So that means that we should be able to set these equal down here. We're going to take x times 4, because those are the two parts of this segment, of this chord, and take that and set it equal to 3 times 8. We can solve this equation for x equals 24 by dividing by 4 from each side, so we'll be left with x equals 6. You can go back and plug it in, make sure 6 times 4 gets us 24 as we thought, and it does, so we know we got it correct. We're going to move to the next one. If you think you can try it on your own, feel free to pause the video and press play when you're ready to check it. So we're going to take 4x plus 2 and multiply it by its other part of a chord, which is 8. And I'm going to use the distributive property to multiply that. For my other chord, I'm going to multiply the two segments 9 and 4x. When I distribute here, I'm left with 32x plus 16 should equal 36x. I'll subtract 32x from each side, so 16 equals 4x. And by dividing by 4 on each side, we'll get 4 equals x. Again, we could check this and make sure, well, this should be 16, and then this should get us 18. So 18 times 8 should equal 9 times 16, and that's how you can verify that your answer is correct. In our last example, we had the segment 2x plus 5 multiplied by 12. Those are the two parts of the segment, or of the chord, and we're going to set them equal to 14 times the other part of its chord, which is 2x plus 2. Again, we need to use distributive property this time on both sides. So we have 24x plus 60 equals 28x plus 28. I'm going to subtract 28, which leaves me with 32, and subtract 24x, which gives me 4x, and by dividing by 4 on each side, I'm left with 8 equals x. Our next theorem today is our segments of secants theorem. And this states that if two secant segments share the same point outside a circle, so in our diagram we have point E, then the product of the lengths of one secant segment and its external segment equals the product of the lengths of the other secant segment and its external segment. So what we mean by that is we're going to be taking this external segment EA and multiplying it by the entire secant segment EB. We'll set that equal to EC, which is this internal segment, external segment, and then we'll multiply that by the entire secant segment, which is ED. So EA times EB should equal EC times ED. That's how we're going to be able to solve for our x's here. We're going to take 6 times 9 plus 6, which is 15, and set that equal to 5 times x plus 5. So we're taking our external pieces times the entire segment, and then the external times the entire segment. So we get 90 equals 5x plus 25 after we distribute. This leaves us with 65 equals 5x, and therefore 13 should equal x after we divide by 5 on each side. If you'd like to pause the video and try the other two, go ahead and then press play when you're ready to check. Next up, we have 4 times the entire segment, 6, so 4 plus 2, and then 3 times the entire segment, which is 3 plus 2x plus 5, which I'm just going to simplify to 2x plus 8. I got the 8 from adding 3 and 5, combining my like terms. So 4 times 6 is 24. 3 distributed to 2x plus 8 gets us 6x plus 24. I'm going to subtract 24, leaving me with 0 equals 6x, and therefore x equals 0. So that should mean that our segment here is actually just 5. So 4 times 6 is 24, and 3 times 8 is 24, meaning that we got the same product, so this is true. Then we have our last one here, so we're going to take 3, which is our external segment, times 3 plus 6, which is 9, the entire segment, and set that equal to 4 times 4 plus x. So we're taking our external times our entire segment. So we get 27 equals 16 plus 4x. I'll subtract 16 from each side, leaving me with 11 equals 4x, and therefore 2 3/4 is our value for x. Our last theorem that we're going to look at today is called the segments of secants and tangents theorem. This is where we have a tangent and a secant working together from the same endpoint, and when this happens, we can say that if they share that external point outside of the circle, the product of the lengths of the secant segment and its external segment, so similar to what we were doing, the EC times ED, is going to be equal to the square of the length of the tangent. And because we don't have that same internal part of the segment like we did above right here where we had like the 6, so we did 3 plus 6, now we're just going to be taking EC times ED and setting that equal to EA squared. So we're going to take our tangent length, which is 6 here, and square it, setting that equal to our external segment length of our secant times the entire secant segment, which is 4 plus x. So 36 should equal 16 plus 4x, 20 equals 4x, and we'll be left with 5 equals x. Here we've got x squared should equal 4 times 9, and I'm getting that from the external, times 4 plus 5. So x squared should equal 36. Take the square root on each side, x is equal to 6. And then last up, we have this tangent, which is 2x. I need to square that entire segment and set that equal to the external times the entire secant segment, which is 13. So when I do that, I'm left with 4x squared equals 117. I'm going to divide by 4, which leaves me with 29 1/4. Take the square root, and so I'm left with approximately 5 4/10 when we round to the nearest tenths place there. This last one is a bit of a challenge here. We want to use our knowledge of circles and the Pythagorean Theorem to find the length of QP. So what we're going to be doing here is noticing what type of segments they are giving us. We can see that QR is a tangent, and so if I name this X, I can do what I was just doing above and say, well, I have a tangent and a segment, or secant, and I can use that formula to help me solve for X. So it should say that X squared is equal to 14 times 26, and I'm getting the 26 by adding those two secant segments together and multiplying by that external segment of the secant. So 14 times 26 is 364, so x squared equals that, meaning x is just the square root of 364. And I'm going to leave it like that for now because that's not what my final answer is, it's just helping me find my final answer. So now that I know that this side is worth the square root of 364, I know that this whole segment PR is 26. This is a right triangle, and I want to solve for this value. I'm actually going to call it y since we already used an x. And that's just a leg in my right triangle. So I'm going to use Pythagorean Theorem. I'm going to take y squared plus the other leg squared, which is 364, the square root of 364. We're going to square that, and set that equal to the hypotenuse squared, which is 26 squared. Simplifying that leaves us with y squared plus 364 because the square root and the square cancel each other out, and that is all equal to 376. When we subtract, we're left with a difference of 312, and we'll take the square root of each side. This leaves us with 312 can be broken up into the factors 4 times 78. So since we can say that that's 4 times 78, that means I can take out that perfect square of 4, make it 2, and leave the 78 inside of the radical, and therefore PQ equals 2 root 78 for our final answer.